Okay, I want you to picture the timeline of human history. And I don't mean the short version you get in, a high school class, the one that starts with the pyramids. I mean the really, really long version, deep time.
Millions of years.
Exactly. Now imagine taking a massive chunk of that timeline, specifically the part about our ancestors first arriving in East Asia, and just realizing you have to rewrite the whole thing.
And we aren't talking about a minor correction here. This isn't moving a date by a few thousand years.
No, this is a seismic shift. As of February 2026, the story of Homo erectus in China has been pushed back by nearly 670,000 years.
It's an incredible number. That is more than 500,000 years of history that sort of just appeared.
For a long time, the Yunxian fossils from Hubei Province were a bit of a question mark. But a new study in Science Advances has completely changed the game.
It's replaced a best guess with hard physics.
We used to think these individuals were, maybe 800,000 years old? Maybe 1.1 million on a good day? But the new number?
1.77 million years old.
Which is just staggering.
It is. It makes them the oldest securely dated Homo erectus skulls in the entire East Asian record. Period.
So today, on this deep dive, we're going to unpack this. I mean, we have to talk about the fossils themselves, because finding 3 skulls in one spot is wild enough.
Oh, absolutely.
But we're also going to get into the science.
Yeah.
Specifically, how researchers used, a quartz clock and cosmic rays to land on that date.
It's a fascinating detective story, really. It blends geology, particle physics, and, our own evolutionary story to solve a puzzle that's been around for decades.
And finally, we have to talk about what it all means. If our ancestors were in China nearly 1.8 million years ago, what does that say about them? I mean, they were true world travelers.
They were pioneers in every sense of the word.
Okay, let's start with the what? The Yunxian fossils. We aren't talking about a couple of random teeth here, are we?
No, and that's what makes this site so incredibly special. Usually when we talk about early human fossils, we're dealing with fragments, a piece of a jaw, a lonely molar, maybe a bit of a leg bone.
And from that, you have to reconstruct an entire species. It feels like building a car from just a hubcap.
It can be, but at Yunxian we have 3 fairly intact crania, skulls. You have EV9001 and EV9002 discovered back in 89 and 90.
Right, those have been famous for a while.
Very famous. But then very recently, in 2021 and 2022, they uncovered a 3rd one.
And it was right nearby, not miles away or something?
No, just 33 to 35 meters away from the first 2. And critically, it was in the exact same sediment layer. Geologically speaking, they were neighbors.
They were buried in what's called a calcareous concretion horizon.
That's it. It sounds like a heavy metal band, I know.
It really does.
But it basically just means they were cemented into the rock. And having 3 individuals from the same site in the same layer, well, that gives you a population sample. It's not just one weird outlier. You're looking at a group.
Okay, so we've had 2 of these skulls for over 30 years. Why was the date such a mess for so long? How do we go from 800,000 years to almost double that?
That's the 1.77 million year question, isn't it? The problem was the context. You can't just radiocarbon date these things.
Right. Carbon-14 is only good for, 50,000 years?
At most. It's useless for deep time. So the methods they used before were, let's call them interpretive. They leaned really heavily on biochronology.
Which is looking at the animal fossils found with them, right?
Exactly. You find a fossilized pig, you know roughly when that pig species lived, so you assume the human skull is about the same age. It's logical, but it's fuzzy. It's like guessing the year of a photo by looking at the style of a suit.
You'll get the decade, maybe, but not the exact year.
Precisely. And the other method, paleomagnetism, was also tricky here. The Earth's magnetic field flips, and the rocks record that. But if you don't know roughly where you are in time, matching that magnetic stripe to the master chart is risky.
So they thought it matched a younger event.
They thought it matched the Jaramillo subchron, which is about 1 million years old. They were sort of forcing a puzzle piece into the wrong spot because the animal fossils seemed to point that way. It was a circular argument.
And that's where Yunxian sat for 30 years. Interesting, but confusing.
Until the new study by Hua Tu, Christopher Bay, and their team, they decided to stop guessing and start measuring. And they brought out the big guns.
Cosmic ray burial dating.
This is where it gets really cool. The technical name is isochron aluminum-26 and beryllium-10 burial dating.
Okay, let's unpack that because it sounds like we're building a spaceship. How on earth does that work?
It's brilliant physics, but the idea behind it is actually pretty simple. Imagine you have quartz minerals, just regular sand or gravel, sitting out on a hillside.
Quartz getting a suntan.
Exactly. While it's sitting there, it's getting bombarded by cosmic rays from space. These high-energy particles slam into the quartz and create two specific isotopes, aluminum-26 and beryllium-10.
So the longer the rock is on the surface, the more of these isotopes it collects. It's like it's charging a battery.
That is a perfect analogy. It's accumulating a cosmic sunburn. But then a geological event happens. A flood, for example.
Which makes sense since they were found in a river deposit.
Right. The river swells, grabs that quartz gravel, washes it downstream, and buries it deep under layers of mud and silt.
And once it's buried,
The cosmic rays can't reach it, the production stops instantly, the battery stops charging, and that's when the clock starts ticking.
because the isotopes are radioactive, they start to decay.
Correct. But here's the magic trick. They decay at different, but very well-known rates. Aluminum-26 decays about twice as fast as beryllium-10.
Ah, so it's not just about how much is left, it's about the ratio between the two of them.
Bingo! Imagine you have two different hourglasses that run out at different speeds. If you know how much sand was in each at the start, and you measure how much is in each now, you can calculate exactly when they were flipped over.
That is incredibly elegant. You're literally reading a clock made of stardust that was buried in mud millions of years ago.
And it lets us date things up to 5 million years old. It bridges that huge gap that carbon-14 can't touch.
So they took quartz from the layer right next to the skulls, that's layer C3, and ran the test.
And the result came back. 1.77 million years, plus or minus just 80,000 years. In deep time, that's a bullseye.
And they doubled down, they tested a deeper layer too, right? Layer C6?
They did, and layer C6 came back at roughly 1.76 million years.
Wait, hold on. I'm not a geologist, but shouldn't the deeper layer be older? If C3 is sitting on top of C6?
Normally, yes. But you have to look at the error margins. You have 1.77 plus or minus 0.08 and 1.76 plus or minus 0.22. Statistically, those dates are indistinguishable. They overlap.
So what does that mean?
It tells the geologist that the whole deposit was laid down incredibly fast. This wasn't a slow dusting of dirt over millennia. This was a rapid burial event, a massive flood season maybe, that laid down all that sediment in a geological blink of an eye.
Which actually explains why the skulls are in such good condition. They weren't sitting out on the landscape getting trampled. They were locked away.
Exactly. Rapid burial is a fossil's best friend.
Okay, so we have this rock-solid date. But I know there are other sites in China that have claimed to be really old. I'm thinking of Yuanmu. Why is this new Yunxian date such a mic drop compared to that?
That brings us to the in situ debate. And if you take one thing away about archaeology today, let it be this. Context is everything.
In situ just means found in place.
Right. Now look at Yuanmu. For a long time, it was cited as China's oldest site, dated to about 1.72 million years. Very close to this new Yunxian date.
So why is Yuanmu still the champ?
Because the evidence there is just two incisor teeth. And crucially, they were surface collected.
Meaning someone was just walking along, looked down, and oh, look, a tooth!
Essentially, yes. They weren't found embedded in the rock. When you find something on the surface, you have to guess where it came from. Did it erode out of that layer over there? Did it wash down from a younger layer up the hill?
It's like hearsay evidence in a courtroom. I think it came from there versus I saw it come from there with my own eyes.
That's a perfect way to put it. There's always a shadow of a doubt. But Yunxian is in situ. Those skulls were hammered out of that calcareous concretion. They were cemented into the rock alongside the stone tools and the animal fossils.
So there is zero doubt which layer they belong to.
None. You date the layer, you date the skull. It provides a level of certainty that a surface find just can't match.
And what about Gongwangling? That has an in situ skull.
It does, but recent dating places it at about 1.63 million years. So Yunxian is clearly older.
So Yunxian is now the undisputed heavyweight champion. Oldest in situ, securely dated Homo erectus in all of East Asia.
It's a new anchor point for the entire timeline of the region.
But this new certainty, it actually creates a new problem, doesn't it? Or maybe it just highlights a mystery that was already there. I think we called it the gap.
Ah, the gap. Yes, this is fascinating. See, we have two types of evidence. The tools, which is archaeological, and the bones, which is paleoanthropology. And in China, they haven't been matching up.
We've found stone tools that are way, way older than these skulls.
Much older. We have a site called Shudu, dated to roughly 2.43 million years ago, and another, Shengchen, at about 2.1 million. At these sites, we have clear evidence of tool making, but no bodies.
So for ages, the timeline was someone's making tools at 2.4 million years.
Right.
Then radio silence for over 1 million years, And then Homo erectus finally shows up at what we thought was 1.1 million years.
It was a huge disconnect. It's a murder mystery where you find the weapon at the scene, but your main suspect doesn't even arrive in town for another week.
So how does the new Yunxian date help?
Well, by pushing the skulls all the way back to 1.77 million years, we've narrowed that gap significantly. We've brought the suspect much closer to the crime scene.
But 1.77 is still a long way from 2.43. That's still nearly 700,000 years.
It is, and this raises what is probably the most exciting question in the field right now. If Homo erectus is confirmed at 1.77, who on Earth was making those tools at 2.4?
Because this species Homo erectus isn't even supposed to exist that far back, is it?
The current consensus is that Homo erectus, or its African counterpart Homo ergaster, evolved in Africa around 1.9 million years ago.
So if they evolved in Africa at 1.9, they couldn't possibly be making tools in China at 2.4. The math just doesn't work.
It suggests a few possibilities. One, the dating of the tools is wrong, but it seems pretty solid. Two, Homo erectus is actually much older than we think. We just haven't found the earlier fossils in Africa yet.
Or
three, the tool makers at Shudu weren't Homo erectus at all. Maybe they were an earlier species, Homo habilis, or something we don't even have a name for yet. Did a different, more primitive human cousin leave Africa long before erectus?
that is wild thought. A ghost lineage exploring Asia 500,000 years before the main event.
It's entirely possible, and the Yunxian discovery is so critical because it clears the fog. We now know, for a fact, erectus was there by 1.77. It gives us a solid floor to stand on while we reach for those much older, deeper answers.
Let's zoom out to the big picture, the out-of-Africa model. How does this new date change that map?
It changes our understanding of the speed of that dispersal. We have the famous site of Dmanisi in the Republic of Georgia. It's right at the gateway between Africa and Eurasia.
Right, and those fossils are dated to about 1.8 million years ago.
Exactly. So at 1.8 million years, they are just stepping out the front door. Now look at Yunxian, 1.77 million years ago. And that is thousands of miles east, deep in central China.
That's basically the same time.
In geological terms, the difference is negligible. It's almost instantaneous.
So what does that tell us about their migration?
It implies a rapid dispersal. Once these ancient humans left Africa, they didn't slowly meander across the continent. They moved fast, they spread across Eurasia incredibly quickly.
They were on a mission.
Or at least they were incredibly adaptable. I mean, think about the difference in environment between the Caucasus Mountains in Georgia and the river valleys of central China. To thrive in both places at virtually the same time means Homo erectus was a generalist.
They could handle different climates, different food sources, everything.
Exactly. They were the first truly global human species, and the Yunxian date proves this global expansion happened almost as soon as they appeared in the fossil record.
I want to circle back to a technical point you made. You said the new cosmic rays study actually helped fix the old magnetic dating, didn't it?
It did, yes. It acted as a calibration. It's a great example of how different scientific disciplines can support each other.
The physicists helped the geologists read their map correctly.
Precisely. Once the burial dating gave them an absolute age of 1.77 million years, the geologists could look at the magnetic polarity of the soil again, and they realized, this layer corresponds to the Olduvai subchron.
The Olduvai subchron. That sounds like a chapter from a sci-fi novel.
It does, doesn't it? It's just a specific period, roughly 1.78 to 1.95 million years ago, when the Earth's magnetic field was normal. Previously, they tried to squeeze the layer into the younger Jaramillo event, but the cosmic ray date proved it had to be the Olduvai.
So they were reading the magnetic barcode upside down because they didn't know what time it was.
In a way, yes. The quartz clock gave them the key to unlock the correct magnetic sequence. It's just amazing how counting a few atoms of beryllium and aluminum can ripple out and rewrite geology, biology, and human history all at once.
That's the beauty of this field today. It's truly multidisciplinary. You can't just be a bone hunter anymore.
Not at all. You need the particle physicists and the geochemists right there in the trench with you.
So let's bring this all home. What's the big takeaway for someone listening? Why does Yunxian really matter?
First, it anchors the timeline. We now have a solid, reliable date for Homo erectus in China at 1.77 million years. No more guessing.
Second, it validates the technology.
Absolutely. This proves isochron burial dating is a powerful tool for these deep time puzzles where other methods fail. We'll probably see it used to reevaluate other controversial sites now.
And third, it just changes our view of our ancestors.
It really does. It paints a picture of them as rapid, capable explorers, colonizing vast new continents almost as soon as they evolved.
And this is the thought I want to leave you with. That gap is still there.
It's still there. It's narrower, but it's there.
We know Homo erectus was in China at 1.77 million years. But those stone tools from Shudu are still sitting there at 2.4 million years, just daring us to explain them.
That is the next frontier.
If Homo erectus didn't evolve until 1.9 million years ago, who was chipping those stones in China 500,000 years earlier? Are we looking for an even earlier Homo erectus migration we just haven't found the bones for?
Yeah.
Or was there a completely different unknown species of human out there exploring Asia while our direct ancestors were still figuring things out back in Africa?
That's the question that will drive the next decade of excavation. And honestly, I think the answer is going to surprise all of us.
And when they find that answer, we will be right here to deep dive into it. Thanks for listening.
Keep questioning.